welcome back to the stream. So let's first see is the stream working or not. Live. Hello, hello. Okay, I think the stream is working. Let's go. So, what's the objective of today? So, today I am going to finish this. Try to get an overview of deep residual. Last time I looked over some of the matrices and I looked at the abstract, and after the stream I also after the stream I looked at some of the matrices, metrics, evaluation metrics used in this, in some background. I did some background study for this paper about how this error is measured. It is a top 5 error, and how what is this 20% really means, what is trying to measure. So there are a few things I understood. Let's me state that pi temp. So I looked at top 5 error rate, and there is also similar term top k error rate, also accuracy rate. So it's the top 5 error rate. It's just comparing your prediction with the top 5 uh, most comparing your prediction to the top 5 your ground to the top 5 prediction rate. So say if you have an uh, animal classification model, so it classifies it into different animal: dog, cat, monkey, lion, tiger. So after the prediction it gives confidence score to the top 5 uh, prediction by the model, and it compares with the ground truth. If the ground truth belongs to the top 5 prediction, then we say it's true positive, and if it doesn't belong to that, we say it as false positive, I think. So this is how we use top 5 error rate, and also there are certain other metrics like IOU, intersection over union. So intersection over union, what it does, it compares whether the prediction and ground truth, whether how overlapping is the prediction box and the ground truth box. So it compares based on a certain threshold. If say your you have an image of a man on image of a man, and there is a rectangular box that identifies the man in the image, and after the prediction your model also draws an rectangular box. So let's see object prediction, let's see. So as you can see, say this cyan color is your ground truth, and this a bounding box, and this yellow is say your prediction. So it checks the proportion of how this intersection parts overlaps. If greater the intersection means more, greater the ratio means the model is has accurately predicted the bounding box of the object. So this helps us evaluate it, this helps us to identify object in image. So IOU, intersection over union, so we compare different models using different thresholds. So if the IOU is above a certain threshold, then we know, then we say that the model is able to predict it. Then I looked at maximum I think suppression, non-maximum suppression. So a model can have model can give multiple bounding boxes for same prediction. So same prediction has multiple bounding box. So rather than rather than uh, how to say that, so rather than looking at all the bounding box, we look at the most appropriate bounding box and remove all the other bounding box around that image. So non-maximum suppression takes the most confident bounding box and removes all the other less confident bounding box. So let's me show you that non maximum suppression. So let's see, yeah. So as you can see, there are multiple bounding box for the same image. So I think we are looking at this band-aid. So the non-maximum suppression will get the best one and remove all the nearby, all the other bounding boxes which are predicting the same thing but with less confidence. So it also uses IOU internally for comparing different bounding boxes. So then after that I looked at average precision. So what average precision does, it takes the, it checks how, it looks at the precision recall curve and calculate how good is the model. So as you can see here is here precision recall curve. So let's say it's the precision recall curve. So at the start, at different threshold, we draw this precision recall curve. It's the how can I, the curve is not so smooth. It looks discrete because it uses uh, whole number to calculate that precision recall values. So when we plot it at different intervals, we get that graph. So the average precision means the area under this curve. So a good model will have an area of 1, so it will be at 1 comma 1, and the curve will be a right angle, upside down right angle. So if we want to compare different model, if models are near this point, the model, if the model has more area, that is if it tries to approach the perfect graph. The perfect graph is, let me see what is the perfect graph. So let me fix. So a perfect model will have So let's say this is the it's black. Let's say this is the perfect model. So this point is at 1 comma 1 comma 1. So this is the precision and this is the recall. To compare the perfect model would have a precision of 1 and recall of 1. That means it is able to properly classify all the true positive, and if the recall is also 1, it means it um, didn't have any false negatives, so it was properly able to classify the true positives, and there are no extra false positive, also no bad predictions, and able to predict all the data points. So this is the for a perfect model. So if we have to compare different model, if different model approaches try to approach this graph. So this is a model A, the green color is a model, the blue is also a model. So when you compare this graph, the more, if a model has more area in precision recall graph, that means it's a better model. So this green is trying to approach this perfect model, right? So if if you see the area under the curve, it will have more area than the blue one. So we can say that the model is a better model. So the average precision is just this area under the curve. So that what average precision is. Then there is mean, average, PRECSI1. So after we calculate average precision for class 1, say we take the graph, we get it 0.3 for say a classification where we classify different animals like cat, dog, and different classes. So it got 0.4, 0.8. So when we take the mean of all the classes, so 0.3 plus 0.4, and take all the classes, average of all the classes, then we get mean average precision, and we calculate this mean average precision at different threshold of IOU. So say the IOU was 0.5. So when we take the bounding box, if the IOU, the intersection and the union is greater than 0.5, then we say it's too positive, and greater than 0.5 too positive. So we say we compare, we then draw the graph of precision recall for the 0.5, and again for different thresholds, say for 0.5, 0.55, let me use a text here. So for 0.5, 0.55, 0.60, 0.90. So at different threshold we draw the precision recall curve, and then we take all the mean, average at different threshold, and we again find their mean. So this gives us and this term at different threshold, and after we get the mean at different threshold, we again take the mean of the means. We first take the average, then we calculate the mean average means for different classes of same threshold, so 0.5. Then we compare at different thresholds, 0.05 of IOU, 0.05, 0.55, and after that we calculate the mean again. So this is called mean average precision at starting from 0.5. At an interval of 0.05 we go till 0.95. So this is a metric used, so I looked into it. So mean average precision, so take this. So these are the metrics used. These are the background evaluation metrics used in this paper. So I looked into all that. So I also don't have quite a good idea about that, but let's see. While I go through this paper, I will search. I will look more into this. Uh, so next, I will look at. I will again start with the abstract. I will look at all the graphs. So today, my objective is to go through this abstract, look at all the graph evaluation metrics, the figures, what are the different model used, and look into the model. What is the data set? Look at the data set. How to read all this graph and all that. Do this graph and conclusions. So let's get started with this. So what so let's see. Let me change this to dark mode. So last time what we did is this was the starting. Deep neural network are more difficult to train. We present a residual network. So just are more difficult to train. Okay. So we present a residual learning paper to be the training of network that are substantially deeper than used previously. We present a residual framework. Okay, they provide us with a residual framework. Use of training. Substantially deeper than used previously. To residual connection to ease the training. Okay. Sorry about that. We provided comprehensive empirical evidence. We explicitly reformulated the layer as a learning residual function. So they reformulated the layer into learning residual function. Okay. So into this residual function. Residual function. I'm also using a paper and pen to write if something is important. So if you see me writing something, don't. If you see me writing something, if you don't see me writing in the this screen, I'm just writing it in my paper. For later reference to input layer. So they form a residual function instead of learning unreferenced function. So from the layer as a residual function. We provided comprehensive empirical evidence showing that the residual network are easier to optimize. You can gain an accuracy from considerable increased depth. Okay, on ImageNet dataset. So they first use the ImageNet dataset. We evaluated the residual network with a depth of 152 layers, x 18 times deeper than VGG, but still have lower complexity. they trained using the network check on a network of layer connectivity layer deeper than BGP but still have lower complexity. Still have lower complexity. An ensemble of residual network achieved 33.5% error on the ImageNet set. 3.5. So this 3.45% is just top 5k error. This result on the first prize in this data set. So classification task. This is a competition that object detection image. This has different classification tasks. So this challenge I think provides CFIR 10 data set. We also presented analysis of CFIR 10 and 100 layers, 10 and 1000 layers. CFIR 10 and 1000. Okay. The deeper representation is of central importance for many visual recognition tasks solely due to extremely deeper representation. So the depth of representation is of central importance. Depth of representation. How deeply you represent the image, right? Solely due to our extremely deep presentation, we obtain 25% relative improvement in the COCO object detection dataset. So it also uses the COCO object detection dataset. So deep residual network foundation offers online and co-production competition, where we also won the first place in the tasks of ImageNet detection, ImageNet localization, and co-detection detection. Okay, so what I understand is, so this paper use some kind of residual learning framework. So rather than normal deep neural network are more difficult. Rather than using a normal deep neural network, it used an residual connection. Okay, and this is reference to input layer, in reference to some kind of connection with input layer. So directly to the input. So and it also trained the data, checked its accuracy on ImageNet, CFIR 10 dataset and also COCO dataset. Okay, and this network, reference network input, and this what it improves the optimization capability, ability for improving for deeper networks. So it 52 layer network. Okay, network is easy to optimize. Okay, deep neural. So deep neural network was hard to train. So what it did is so deep NN replace with residual connection, right? So why hard train. Deep neural network is hard to train. So we used residual connection on input data to ease to improve to improve optimization. Okay. Optimization. So that's what the paper talks about. So it tested the data on COCO dataset, CIF, AR, CFIR, CFAR 10 and ImageNet dataset. Okay. So also it uses it trained the model on 152 layer data. So that what's it talks about, right? So this is what it is. So I have to now look at what the COCO dataset has. COCO, CIFAR 10 and ImageNet dataset. So I will now look into this, what these are, what are those. So before that I have to see what do you mean by unreferenced function, referenced and unreferenced function. Look at all way to so there is a graph here. Let's see what is talking about. Train error left and test error right on CFIR 10 with 20 layers and 56 plane network. So training error, this is the training error graph, it is a test error graph. So I think it is the iteration, number of iteration. It was trained on 10 power 4. So 1 into 10 power 4. So it is trained till 60,000 iteration. We tested it also different iteration. So we should have plane network without residual connection. So the training at plane network. So it is typically believed that deeper network will have less error, but contrary to what we believe, this 20 layer network has less error. As more we train the network, less the error, and there is steep decline in error rate here after I think 30,000 iteration. To look at this, deeper network has higher error, thus test networks similar phenomena on ImageNet present in figure 4. So this is quite peculiar, right? So shouldn't the 56 layer have more error or less error because it has higher layer, deeper representation of an image, but no, this has more error. So this more what do you say, more reinforced our evidence that deeper neural network are more difficult to train. Because of the difficulty of training, I think this error rate result is, I think somehow the residual connection and try to improve it. This graph, right? hmm Let's go deep. Let's see. So this is a residual learning building block. So we have an X here. We pass it through a layer. We get an we then get ReLU. Pass it through ReLU. We get the logits. Then with that we add this X, right? So this is quite different. So we again add the same building block. How is this better than other? F and f of x plus 1. If we differentiate it in terms of weight, wouldn't it be 0 because it has no connection between weights? Only the value is increased, right? Hey, एक second.